Hey there, welcome back to 2241. This is our examples 2 video for section 2.3, and we're going to continue with some more examples involving motion in space. All right, problem number 5 here gives us a baseball, says it's thrown at a specific angle phi relative to the ground, and it has an initial speed of v0. What do they want to know? What angle phi maximizes the horizontal distance traveled? Let's draw a quick picture of what's going on here. We've got the ground here, and we have an initial velocity. So maybe the baseball is launched here at some speed, and we'll call that v0. And then right here, we have the angle that the baseball makes with the ground. Okay, and then what happens? Well, you launch it at some speed, and it travels in sort of an arc shape. If you've ever thrown a baseball, you're probably familiar with this. And lands on the ground somewhere over here. Okay. There's a diagram of our situation. Now, we have a maximum height here. That's not what I wanted. Maximum height here, and a maximum distance. So when the ball hits the ground, how far did it go? Okay, so, well, the first thing that we might want to do in any one of these situations is just set up Newton's laws. So if we just write down the law itself, we're given that F equals mass times acceleration. Okay, and this has two components now, so we can split this into two equations. One in the x direction, we'll say this is x, and this is y. So in the x direction, we have Fx equals the mass times the acceleration in the x direction. And y says Fy equals the mass times the acceleration in the y direction. Okay. Well, let's focus on the y direction for a second, because that's where we have some actual forces going on. In the y direction, we have the force of gravity acting downwards there. So our acceleration in the y direction there is going to be minus g. So we have Fy equals m, or m times minus g, or just minus mg. Okay. And now what we can do is note that we have no acceleration in the x direction, and do some integration, so some vector integration like we've done already. So here we've got that our acceleration vector is equal to the force vector divided by the mass. And our force vector was, well, we've got no forces in the x direction, a force of minus mg in the y direction, divide by m, and we get the vector 0 minus g. Okay, and that should make sense. This vector that I've drawn is length g. It's pointing in the negative y direction. So we have a y component of minus g and no forces in the x direction. All right, well, how do I get my position vector? I integrate. So my velocity vector. My velocity vector is going to be initial velocity plus the integral from 0 to t of a, and then ds. So if we plug things in here, well, v0 is some vector. v0 is let's say let's leave v0 for a second, and we'll deal with that later. So v0 is just going to be v0, and then we want to integrate from 0 to t 0 comma minus g ds. Right. And now we can integrate this. Hopefully this is relatively easy. We have v0, and then the integral of the 0 function over any interval is just 0. So this is going to be plus 0, and then minus g times t. Okay, so there's our velocity as a function of time. All right, and now to get our position, what do? Well, same thing. We're just going to take the integral from 0 to t of our velocity function. Velocity ds. And this is, okay, well, r0 is 0. Why is it 0? Because I've chosen my coordinate system so that the initial position of the ball is at the origin. So coming back over here, we have that our position is just the integral from 0 to t of the function 0 minus gt d, or gs, keep doing that, gs ds. Okay, and we get minus 1/2 g t squared now. Oh, and I forgot my velocity, my initial velocity, sorry, plus v0 ds. So we got to add that part in here. Plus v0 ds. This is a constant vector, so I'm just going to multiply it by t in the integral. So v0 times t, and then we have our velocity or position function as a function of time. Okay, so now we have our position, and we can start to think about what's going on with this vector v0 right there. Well, we have a coordinate system set up, and hopefully you remember how to find the components of any vector given a coordinate system and its norm. This is going to be the norm of the v0 vector times the cosine of the angle that it makes with the axis. And this is going to be the norm of the vector times the sine of the angle that it makes with the x-axis. Okay, so these are your direction cosines or sines. But wait, remember that the norm of the initial velocity is just the initial speed. So we have v0, which is known, times the cosine of phi, and then comma v0 times the sine of phi. Okay, so now we've got our position vector and our velocity vector in component form, and we can write r of t equals 0 comma minus 1/2 gt squared plus v0t, but v0t we've written in component form with v0 cosine, v0 sine, and then times t. Okay, so then finally our position vector at time t is given by the full component form v0 cosine of phi t, put some parentheses in there, and then minus 1/2 gt squared plus v0 sine of phi t. And this is our x and y component as functions of time. Okay, so those are our parametric equations. I said we'd derive those in the overview video. And now what do we want to do with them? Well, we want to find the maximum distance. So when the value of x when y is 0. Okay, so I said that we would derive our parametric equations for projectile motion. That's what we've done. And now we want to find the maximum distance that the ball travels. And that is going to be the value of x when y is equal to 0. Okay, so what can we do here? Well, there are a couple of different ways to go at this. We can solve for t directly when y is 0. So if y equals 0, then we have minus 1/2 gt squared plus v0 sine of phi t. Okay, but we can divide a factor of t out of here because the t equals 0 solution is the initial position of the ball, and we know that that is 0, and that's not where the ball has traveled at all. All right, and so that gives us an equation we can solve for t relatively easily. So we get t equals v0 sine of the angle times 2 divided by g. And so that's our value of time when the ball hits the ground. And so we take this and we plug it right into x. So x of, let's call this t star maybe. X of t star equals v0 cosine of phi times the t star value, which is 2v0 sine of phi over g. Okay, and so our final formula here is 2v0 squared sine phi cosine of phi divided by g. And if you're familiar with some trig, you might remember that you can rewrite that as a double angle. And so now we can think of x as a function of the angle phi, because remember, phi has been a variable throughout this whole thing. I haven't even dealt with it. It's just been some arbitrary parameter. And now I want to know what value of phi makes this function a maximum. Well, there's one way to do that, and that's by taking derivatives. So we can take the derivative of this guy, and oh, actually, we don't have to do that. We can just note that the sine function has a maximum. So sine of x, or I don't know, sine of z has a max when z equals pi over 2. So at the top of the unit circle. Okay, well, if z equals pi over 2, then 2 phi is our z, and so we want 2 phi equal to pi over 2. Well, that tells me that phi should equal pi over 4, or 45 degrees. So the distance that a projectile travels is maximized at exactly a 45-degree angle to the ground. Given no air resistance or anything, of course, but this is pretty good as an approximation. Okay, so that solves that problem for us. Next, we have another projectile motion problem. This one gives us some actual numbers. So it says a rock is fired from a slingshot with an initial speed of 150 meters per second at a 45-degree angle. Okay, so it's going to go its maximum distance. If the rock is fired from 10 meters above ground level, then find the distance and speed when the rock lands. Okay, now we have some parametric equations. We can write them down. X of t is v0 cosine of the angle phi times t. Y of t is minus 1/2 g t squared plus v0 sine of the angle phi times t. Except now our projectile is being fired from above ground level. And so we need to do something else here. We need to modify our y with a plus 10. So our initial position is, let me draw this again, is not ground level here. It is right here. And so our projectile is doing something like this. And our initial position is 0, 10. Okay, so if you go back to our previous problem, you note, okay, well, when I looked at integrating v to get r, the position, the initial position canceled out because I set everything to 0. But now this shouldn't cancel out and I get 0, 10. Well, that just gets added in to the equation here. So that's what's happening in this problem. I've just added in that extra term with 10. Okay, so now I'm given all of my parameters. I know V0 equals 150 meters per second. Phi equals pi over 4 or 45 degrees. And G, I know, is 9.8 meters per second squared. Okay, so we're almost there. Now, impact, when does the ball hit the ground? Again, when y equals 0, or not ball, the rock. So the rock hits when y equals 0 yet again. So if y equals 0, then we have 0 equal 1/2 g t squared plus v0 sine of phi t plus 10. Okay, and now I've got to solve this for t. Okay, well, that's a little bit ugly, but we can at least simplify things a little for ourselves. If I if I multiply by minus 2 over g, I can cancel that leading coefficient and make it a monic. And so I get t squared plus, not plus, minus 2v0 sine of phi over g, that looks familiar, t minus 20 over g equals 0. And now I solve this for t. Well, unfortunately, that's going to require the quadratic formula, but let's go ahead and write it out at least. So we have t equals 2v0, a smaller pen here, 2v0 sine of phi over g plus minus the square root of 4v0 squared sine squared of phi divided by g squared minus 4 times negative 20 over g. So I'm going to have plus 4 times 20 over g. And then divide everything by 2. Okay, so a lot going on here. Let's bring this up and clean it up a little bit. So t is equal to v0 sine of phi over g plus minus, let's see, if I bring this factor of 4 out, it'll cancel with the 2. And so I have square root of v0 squared sine squared phi divide by g squared plus 20 over g. All right, we're getting somewhere. Let's see, we've got, okay, maybe we can start plugging in for sine. So if phi equals pi over 4, sine of phi equals square root of 2 divided by 2. So we have square root of 2 v0 over 2g plus minus square root of 2 v0 squared over 4g squared plus 20 over g. All right, getting a little better. Let's see, so the 2 and the 4 will cancel and give us a 2 there. Over 2g plus minus square root, and let's have a common denominator of 2g squared, which means that I need to multiply this by 2g. So we have square root of v0 squared plus 40g over 2g squared. And actually, let's go ahead and multiply that 2 back in. We shouldn't have canceled, so that we can have 2g on the bottom of everything. And we'll get t, again, t star equals the square root of 2 v0 plus minus the square root of 2 v0 squared plus 80 g over 2g. And I guess if you want, you can factor out a root 2 from this thing, but I'm not too concerned about that. All right, so at this point, you might want to plug things into like a calculator because the numbers are not going to be particularly nice. But I can write it out. And actually, yeah, let's go ahead and factor out that root 2 over 2. So root 2 over 2 times 150 meters per second for v0. And then I'm just going to take the plus version because I want the larger time. I don't want the smaller time when the ball hits the ground. Rock hits the ground in this case. And then square root of what's 150 squared? I don't know. 22,500. Okay. Plus 80 times 9.8. Okay. And then divide by 9.8. All right, so this number should come out to be something around 21.7. And so if you go ahead and take this, plug it right back into x as a function of t, so x of t star, we get, let's see, so x of t, where's x? 150 cosine of pi over 4 times t star, or this is root 2 over 2, So we have 75 square root of 2 times about 21.7. So approximately equal to this. This should be in meters, just to double check our units. And this comes out to about 2,300, so 2,306 meters. That's a really, really fast rock, really strong slingshot. Okay, so there's one thing that we needed, and the last thing that we need is the speed when the rock lands. Okay, that comes from our speed function. So we have our parametric functions for position, but if you remember the last problem, we also have our parametric function for velocity. So we can write those down real quick. We have v x of t equals v0 cosine of phi plus 0 vy, not vx, of t equals v0 sine of phi minus 1/2 gt, not t squared in this case. Oh, and actually, sorry, not 1/2, just gt, minus g times t. Okay, now we need our speed function. That's going to be the square root of the square of these two things. It's the norm of the vector. So we have square root of v0 squared cosine squared plus v0 sine phi minus gt squared. Note you have to square the whole component there, not just each one. And this should give us, let's see, v0 squared cosine squared plus v0 squared sine squared minus 2g v0 sine of phi times t. And last, plus g squared t squared. All right. Well, I know that I can factor out of v0 squared, and then cosine squared plus sine squared is 1. So I can simplify this a little bit to v0 squared minus 2 v0 g sine of phi times t plus g squared t squared. And if we're a little bit clever, we can factor out a g squared from every term here. We'll see some stuff that looks familiar. So we have g times the square root of v0 squared over g minus 2 v0 sine of phi over g, v0 squared over g squared times t plus t squared. Okay. And now we remember what some stuff is. So we have v0 and sine of phi. And then our value for t, well, that was the 21.7 thing, so we'll get that in a second. But let's just write this down. V of t star equals 9.8 times the square root of 150 squared, so 22,500 over 9.8 squared. I can't remember what that is. Minus 150, or let's see, 2 times 150 times the square root of 2 over 2, divide by 9.8, and then my value of t, plus 21.7 squared. And if you go ahead and, again, throw all this into your calculator after simplifying, you should get something around 151 meters per second. So a little bit of work there, but good problem to have some experience with. Okay, so that brings us to our final problem of the video. That is, a particle travels in an accelerator with this position function. Find its tangential and normal components. Okay, well, we have formulas for those. I'm not going to try and rederive everything in this problem, so we can just plug them in directly, but we should probably write them down first. So the tangential component of acceleration is going to be r prime dot r double prime over the norm of r prime. And then the normal component is the norm of r prime cross r double prime divide by norm of r prime. Okay. And so this gives me an inkling of what I should do. Probably start by computing the first and second derivatives of r. So this is going to be 2t, 2t, 3t squared. And then my second derivative is 2, 2, 6t. All right. So I need r prime dot r. R prime dot r double prime. And that's pretty straightforward. I just go across vertically, and then I get 4t plus 4t plus 18t cubed. So this is 8t plus 18t cubed. And then I will also need the norm of r. Or let's compute the norm of r. Nah. Let's compute r prime cross r double prime right now. That'll be a little easier later on. So 2t times 6t, 3t squared times 2. So we have 12t squared minus 6t squared is 6t squared. And then 3t squared times 2 minus 12t squared. So we have negative 6t squared this time. And for our last component, we have 4t squared minus 4t squared, which is just going to give us 0. All right, so there's our cross product. And now we need its norm and the norm of r prime. So this guy's norm is the square root of 36t to the fourth plus 36t to the fourth plus a 0 squared. So we just have the square root of 2 times 6, or 6 root 2 times t squared. And then the norm of r prime is square root of 4t squared plus 4t squared plus, and now we do have a z component, 9t to the fourth. That is absolute value of t, square root of 8 plus 9t squared. All right, so that is our norm, and we can just plug things directly into our tangential formula and our normal formula. So r prime dot r double prime is 8t plus 18t cubed, divide by our norm, which is this thing, absolute value of t, square root of 8 plus 9t squared. Okay. And there is something that we can do here. If I factor out a t from the top and bottom here, we have 8 plus 18t squared over square root of 8 plus 9t squared times t over the absolute value of t. And if you're not familiar with that, it turns out that when you divide a number by its absolute value, you just get the sign of the number. It's either 1, -1, or 0. And so we get the sign of t as our last factor there. All right, and then finally we compute our normal component. So we need the norm of r prime cross r double prime. Well, that was 6 root 2t squared. Divide by absolute value of t, root 8 plus 9t squared. If you want, you can also do the same trick with the sine function up here, down here, but you will get something interesting. So let's say we have 6 root 2, 1 factor of t over 8 plus 9t squared times t over absolute value of t. Okay, and just like before, this is the sine of t, but now we have t times the sine of t. Okay, so if t is negative, then I multiply by a -1, and if t is positive, I multiply by a +1. So this is exactly equal to absolute value of t. Well, okay, that kind of makes sense. If t over absolute value of t is the definition of the sine function, well, you just multiply the absolute value over. Okay, so what do we have here is that the normal component is 6 root 2 absolute value of t divided by square root 8 plus 9t squared. Okay. And note that this is the curvature times the velocity squared. And this is the, or sorry, not the velocity, the speed squared. And this is equal to the speed's derivative. So if you can find the antiderivative of this, then you know what v squared is, and you can divide out and find the curvature immediately. I'm not going to try to anti-differentiate this right now because that'll be a little bit of work, but you can do it with some trig substitution and kind of thinking about the sine function there. And then once you have that, square it and divide this thing by it, and you get the curvature.